If everybody would like to find a spot, we'll start. And don't find my spot, Paul. I'll leave that there. Okay, well, I'd like to introduce Dr. Robert Simcoe. Rob received his PhD from Caltech in 2003, working with Wal Sargent. And since that time, he's been at MIT, our neighbor, for the past 14 or so years. First as a Pappalardo fellow, and then as an assistant associate professor of physics at MIT. And this year, he's even closer to us. He's on sabbatical at the Radcliffe Institute. And Rob is well known as both a talented instrumentalist and observer. His scientific interests, not surprisingly judging from the talk today, have centered on heavy element enrichment in the early universe. And in the instrumental side, many Magellan users are very grateful for his development of FIRE, a superb infrared spectrograph. And I believe that FIRE observations are going to feature prominently in today's colloquium. Rob is currently the chair of the Magellan Scientific Advisory Committee, and he also serves on the Giant Magellan Scientific Advisory Committee. His title today is Heavy Element Enrichment in Early Circumgalactic and Intergalactic Environments. Rob.
Thank you very much, and thanks for the invitation to come and speak here. One of the things that Dan might not have mentioned or might not have even known is that even before all the things you had mentioned before, I was an SAO summer intern here, and my advisor was none other than Kim McLeod. So what goes around, it's all in the family, I guess. Speaking of which, there's another Robert Simcoe who works here too. If you came expecting to see him talk, you should leave now. But no, it's kind of a fun thing that there's so many connections like that. Of course, he works over in the plate archives, which is something that is fun to talk about, but different to what I will be discussing today. So in my talk for today, I'm going to focus, as Dan said, on results that have been obtained with the FIRE infrared spectrograph on Magellan telescopes. And in particular, I'm going to use it to discuss surveys for absorption lines that are becoming fairly substantial now, where we can study the redshift 5 and higher IGM. In particular, I'm going to talk a little bit about the evolution of ionization conditions in what is really circumgalactic absorbers. I wouldn't talk about this as the truly tenuous intergalactic space that's well outside the real radius of galaxies, but it's more like the environments you should be thinking of today are comprises loosely bound gas that's in the outer halos of galaxies. It's either just inside the virial radius or maybe just outside, but it is in the immediate proximity of galaxies, and yet outside their disks. And then also, I'm going to talk a little bit about some challenges in the physical interpretation of some of these absorption line diagnostics. Besides the usual challenge, which is that you only get one line of sight through, you basically have a skewer that you're using to probe the physical conditions. There's also some challenges with the physical modeling that I want to highlight. And I should mention what these plots are. We'll learn a little bit more about them later on, but this is from a paper written by Josh Suresh, looking at metal enrichment in cosmological simulations done here. These sort of describe two different ionization states of the same halo of gas as it would be seen in what we call low ionization absorption here, and high ionization. And the interplay between those is going to be a theme throughout this talk. I should thank, before I get started, because otherwise I would feel terrible if I ran out of time. There's a huge number of people that have contributed to this, both on the side of making the instruments that you'll hear about today, from Gabor Firez, Mark Egan, Drew Malonis, and Tim Hellickson, my current team there, and folks who have worked with me and are known to folks here, including Matt Smith, John Bachansky, Jason Fishner, Adam Bergasser, who was at MIT at the time that we built FIRE, and he was a co-conspirator in that, and Paul Schechter as well. And then a group of students and postdocs, some of whom are at MIT, and an undergrad here, Stephen Chen, who's done a lot of the work that you'll hear about today, and Paul Torrey, who's known well to you guys here, has helped with some of the theoretical interpretations. So thanks all to this collection. This, as Dan mentioned, I had been involved in the construction of the Fire infrared spectrograph, which is now been on the Magellan telescopes for 7 years. And it just seemed like it was time for a status update as far as what have we been doing with it in that interim time. So this is me 7 years younger, actually a little bit more than that. And this gives you a sense of the scale of the instrument. It's a cryogenic infrared spectrometer that goes from 0.8 microns to 2.5 microns. And this is it just before it's been buttoned up. The slits would be over here, and then this is the collimator. Then there's prisms for cross-dispersing because it's in a shell spectrograph. That's the E in fires for a shell. Grading here back through the prisms, and then the detectors over here. This is the Hawaii 2RG detector that sits behind this camera where the spectrograph comes to a focus. And so there it is at Magellan. It's on the Bada telescope. It's sitting on this one, and it's been in continuous operation on one of the folded ports. So the elevation bearings of the telescope are here and here, and fire sits in between the two. And has been only off the telescope for a 1-week servicing in the time since it was commissioned in 2010. That was a scheduled servicing. It was sort of like the 50,000-mile tune-up. Now, it was designed, there was a specific reason that I had gone about building this spectrograph. I had done my PhD thesis research on quasar absorption line spectra using the high-res spectrograph on Keck. And we had worked up to a redshift of about 4 to 5 or so. But it was becoming quickly apparent that if you wanted to study heavy element enrichment in the very early universe, people were starting to discover quasars that were around redshift 6 or so. And the heavy element lines for those are becoming shifted into the infrared, as I'll show in a minute. But just for those of you who are not familiar with the technique of quasar absorption line spectroscopy, or who have not seen it in a while, this is just a little cartoon that sort of shows you how it works. That if you have the intrinsic spectrum of a quasar, as you would see it here, this would be as you would see it if it was not transmitted through any intervening material between us and the quasar. This is what it would look like. You would see, if you actually looked with your eyeball at the spectrum and coming off of the telescope, you'd see a bright emission line that corresponds, in this case, to hydrogen, Lyman alpha. And then you would see to the right of this, redward would be things that are at higher redshifts. And then there's some other emission lines that correspond to heavy elements. And these are at the redshift of the quasar itself. However, the thing that's of interest to me is that in reality, it's always the case that you observe these things transmitted through the intergalactic medium. So here's a large simulation box giving you a representation of what the universe would look like, where each pixel on this is about the size of a galaxy. And as a quasar's light traverses from its point of origin to the Earth, if we observe it over here, then at the locations where you intercept one of these filaments, where there's baryonic material, the baryons are going to absorb light from the quasar spectrum, and the most common of those being hydrogen, of course. And so at all redshifts leading up to the redshift of the quasar itself, you can see absorption from neutral hydrogen. And in some cases, those absorption lines are narrow, as you'll see narrow lines through here. Those correspond to just general filamentary structure that is of about the cosmic mean density at these redshifts. And then occasionally you'll pass close by to a galaxy, and then there will be a region of much higher hydrogen density, and you'll absorb something that looks like that. This would be either a Lyman limit system, we would call it, or a damped Lyman alpha, where it cuts out more of the light. But the amount of absorption is much less to the right of the Lyman alpha peak, because that's stuff that's behind the quasar. But of course, there are some lines that you see in absorption here, and those are coming from heavy elements that have rest wavelengths, or laboratory wavelengths, corresponding to electron level transitions that are different to the ones that you would get from hydrogen, the nominal 1216 Lyman alpha transition. So if those are redward, then you can see them. It's not that they're behind the quasar, it's that their rest wavelength is redder. Okay? And so what I'm interested in doing primarily, almost all of today's talk will be focused on the lines that you see out here that correspond to chiefly carbon in the triply ionized state, which we call carbon-4, and magnesium in the singly ionized state, which we call magnesium-2, and the sort of relative importance of those different transitions. Okay? And so FIRE was really designed to do this kind of work, where you're looking at not necessarily a quasar, but the stuff that sits in between. But we're interested in doing this as you approach the epoch of reionization at redshifts 5, 6, and now 7. The other thing that's interesting here is what do you see? So basically what we have is a skewer that's going through the universe. And in these rare cases, you actually come near a galaxy. And I've said that before that those strongest absorption line systems are coming from when you pass close by to a galaxy. And in some cases, you might even go through its virial radius or so the sort of outer halos. So it's a purely probabilistic exercise where you're throwing darts at a board and saying that some fraction of the time you're going to hit a galaxy as you go through the universe. But the thing is, what we see in absorption from these different species, so we see, each chemical has its own spectroscopic fingerprint that we look for by searching for combinations of lines. But what we see is actually a mixture of different physical processes that are happening in galaxies. And in some cases, what we see is informed by simulations that people have run of galaxy formation. This is one from the FIRE simulations that's well known, run by Phil Hopkins and Claude-André Fauché-Giguère and company. Here, this is FIRE as the simulation, not the spectrometer, of course. But the things that we can see in quasar absorption have a particular temperature that's associated with them. If the gas gets too hot, then it's difficult to see in the lines that we can detect, these magnesium and carbon and other lines that we talk about. And by the time it gets to 1 million degrees or so, it's very hard to see. So we see things that are sort of like 10,000 degrees. And so you can watch as a galaxy forms, parcels of gas. I'm going to set this movie going, and you can watch parcels of gas fall into the middle of a halo. Here with the dotted circle, you see this is the virial radius, so the sort of dark matter halo radius, or the gravitational radius of this object. And of course, that's much larger than the disk that's going to form just in this central area. But you'll see that that whole virial volume gets filled with gas, which eventually heats up. But the stuff that isn't hot, we generally can't see. So the stuff that's in this color is going to be invisible. But look for the green, and that's the sort of stuff that we can see. Now, what we're seeing is a mixture of all these different processes, which at very high redshift, so you see the redshift is counting down towards the present. You see stuff that's streaming in from the outside and going through the virial radius and making its way into the central disk area. But once it reaches the central disk, like all modern simulations, this has an implementation of feedback from star formation that heats the disk, and in some cases can eject material. There you can see material that's ejected, but then remains bound and then falls back. But in some cases, you can unbind stuff, and it makes its way out of the halo, and then there's stuff that falls in as well. Okay? But over time, what you see is that it evolves into something where you can, there's this green stuff that's visible in absorption that stays towards the middle, but then you're filled with a hot halo that occasionally can have large streams that would be visible in absorption. Okay? So it's some mixture of this, and what you see from shooting a random dart at this is going to depend on what part of the halo you go through and what condition it's in. But it's not always easy to say, are you looking at stuff that's flowing in? Are you looking at stuff that's flowing out? It's a tricky question to answer. But this is one of the only ways, because the stuff that you see out here, this baryonic material, does not emit its own light at levels that are easily detectable. People are trying to do this now, but it's a very challenging observation. But one of the things that's tricky is if you look at this halo at redshift 0, you see it's all filled with this hot gas, where actually when we look at halos, we can actually see empirically that there are clumps of cold gas that are populated all throughout here in the ions that we'll talk about today. So how you actually produce that is an interesting question. But I just kind of wanted to set the table so you can see what's the experiment we're doing, right? So we're looking at random objects in the background that we're not particularly interested in their properties, only that they allow us to study the intervening material. And the intervening material includes stuff like a galaxy like this. And we're interested in having access to the physical diagnostics of what's happening with gas that's flowing in and out of these galaxies, both in terms of its temperature and in terms of how the gas that falls in is enriched by chemicals formed in the stars that subsequently go to pollute the surroundings. Okay, so furthermore, what we see actually depends on, we don't actually have access to, we can't put a thermometer in there and measure the temperature. And instead what we can do is observe in lots of different ions. Okay, and so this is, if this looks complicated, it's because it is. But there's some terminology that I want to kind of introduce here that we'll be using throughout the rest of the talk. And we can see multiple ions. So when we look at a galaxy halo, we often talk about them as being a system that we find based on magnesium 2 or based on carbon 4. But in fact, the halo has all those chemicals that are in it. And the way that it presents to the observer depends upon the physical conditions, the temperature, the density, and also the radiation environment in which that object is found. And the radiation environment matters a tremendous amount because what happens is because the densities are so low in these circumgalactic regions, you can be multiply ionized before you have recombinations. So if the density is low, you can have a single ionization, for example, let's do an example where you have carbon-2. So ionizing carbon from its neutral state, carbon-1 to carbon-2, singly ionized, happens with a low-energy photon. And then the question is, can you go from carbon-2 to carbon-3 by kicking off another electron? Well, in order for that to happen, you have to have a photon that has an energy of roughly 1.7 something Rydbergs to ionize from carbon-2 to carbon-3. And you have to see that ionizing photon before you get a recombination with another electron. So the density has to be low, and you've got to have enough of these photons at the right energies floating around. Okay? And then likewise, if you want to produce carbon-4, then you've got to ionize it yet again. And so you've got to go from carbon-3 to carbon-4. So now that you've got a carbon-3, then before it can recombine with another electron, it's got to see a photon of roughly 3.5 Rydbergs. Right? So 1 Rydberg is 13.6 eV. It's 1 ionization energy. And so if the density is low enough, then you can have multiple hits of a photon, but they have to be of the correct energies in order to produce these things. Okay, and so which ions you see, so if you see a carbon-4 system, it means that the density is sufficiently low, and the mix of photons that's around is sufficiently broad in its spectral energy distribution so that you've got photons coming in at 0.5 Rydberg, 1 Rydberg, and 3.5 Rydberg. Okay? And so not all different kinds of sources can make those photons. And so the relative balance you get of all these different things doesn't reflect that there's just one chemical there. It's just that the ones that you see are the ones that the particular conditions produce. And here, what I've shown are 3 different spectra as a function of redshift of if you're sitting outside of a galaxy, you're not only seeing starlight from the galaxy itself, but you're seeing the integrated radiation from all the objects in the field that are around it shining from the outside in, because most of these things are optically thin, at least at lower redshift. And so it's going to be the case that the gas that you see is responding to that external radiation environment, which is changing as a function of redshift. In this case, as you go from redshift 3.5 to 4.5 to 6.5, this is sort of the redshift range we're going to be spanning. And a few interesting things happen. One of the most interesting is that at 4 Rydbergs and above, you see the intensity is dropping off as you go to higher redshift, and that's from helium-2 absorption. So it's becoming neutral. But then there's also some other activity happening in here so that the shape of that spectrum is changing. And so that gives us access to this information. So it may be that what you're seeing is modulation from the external intergalactic medium is sort of filtering photons, making their way from sources all around. Or there's also variations you can get because the sources themselves may be emitting at different frequencies. Okay, so here's another busy plot. But the basic idea is that you can get all kinds of different sources that are resonant with all these different transitions that you see here. So don't pay too much attention to the details of this. I talked a little bit about it at lunchtime if you were at that talk. This is the same plot. But the point is, if you have a star that has 3% solar metallicity, it will have one particular kind of spectrum. And as you go down in metallicity to 1/1000th of solar, then the star is going to emit a harder spectrum because in some cases it'll be more massive. And then you see a gray band that's here, and that corresponds to AGN, so it's basically black hole radiation. And that has a yet harder spectrum where there's more and more energy out at large energies. And so at lower redshifts, the photons that ionize carbon-3 to carbon-4, for example, they're coming out here, and they're mostly supplied by AGN. But as you go back to higher redshifts, we're interested in knowing sort of how the balance of all these things changes with respect to each other. Okay, so that tells you sort of the microphysics of what's going on, where you have all these different, there's individual atoms and they're changing their energy levels in response to the density field recombinations and the photon flux that is incident upon them. But what is the sort of environment in which you're finding yourself for these? And this goes back to the plot that I showed you at the beginning of the talk, where there's a simulation of a 400 kiloparsec box. And this shows you, as a projection through that box, what a map of singly ionized carbon would look like in terms of its absorption line strength. And here you see this circle again, which represents the virial radius of the galaxy. And here you see a map of the same galaxy in triply ionized carbon, carbon-4. And the picture that you should have in mind for a lot of these galaxies is that this stuff that has what we call low ionization, so I call things that are ionized by photons of less than or equal to about 2 Rydbergs, the low ion species, and roughly things that are higher than that are high ionization. So silicon-4, carbon-4, those things take a lot of photons to ionize, and the other things are more or less neutral. And so the more neutral stuff tends to coalesce in the middle of galaxy halos. And the reason for that is primarily because the density is higher, okay? And so you're more likely to have more recombinations, and because that density is higher, the odds that you'll have multiple hits and multiple ionizations goes down. Whereas when you get to the outer parts of halos, then the recombination time goes down because it goes down as the density squared, and you end up with the carbon that's out there presents as triply ionized rather than singly ionized. Okay? So that's kind of the picture you should have in mind. And this is something that many people have learned, but it's worth reminding ourselves. The basic idea hasn't changed that much in 20 or 30 years. It's become more sophisticated with better simulations. But the point is that if I shoot a random sight line, if I take a quasar from afar and then I shoot it in at the board, the odds of actually, if you throw a dart, the odds of getting this are better than the odds of getting this. And so when I do random surveys through the universe, and then I start counting up how many varieties of different absorption lines I see, then I expect to see more of these. It's a cross-section selection, and it tells you something about the ionization conditions in these halos. So this is the number that you see depends on the co-moving number density of the halos times the distance. The distance in x is just sort of along the line of sight, correcting for there's a co-moving correction that goes to it. But then ultimately it's this cross-section which is telling you the sort of likelihood that you're going to hit something in this box. Okay, so there's the different ionization corrections, different ionization states, or the levels, trace different scales in the halo. So this gets back to what I was saying before, though, that if you want to go back towards the epoch of reionization, which is a period when we actually think that the ionization state of the universe is actually evolving in a significant way, you really need to be using infrared spectroscopy. And you can see that here where we just take 3 different real quasar spectra. This is at redshift 3.1, 4.8, and 6.1. This isn't even that high anymore. But it's a high signal to noise example, so it's particularly illustrative. Now you see that there's 2 things happening. One is that everything is shifting to the right, but because the universe is becoming more neutral, the Gunn-Peterson trough, or the so-called Gunn-Peterson trough, is starting to appear. And this is actually close to 0 flux all the way up until you get to the Lyman alpha transmission, or the Lyman alpha peak. So everything that you see to the left of here, it doesn't have to be completely neutral. It only has to be 1 part in 1,000 or 10,000. But that's enough to make it black over here, so that all the light from these early objects comes out in the infrared, which is why we built this spectrograph. And the times that we're talking about, just for reference here, is the reason we're interested in this subject, is that the halos, by the time you get to redshift 6 or so, the universe is only a gigayear old at that time. So you're looking at some of the earliest portions of the sequence of formation of the first galaxies. Okay, but we know that there are some that exist at higher redshifts, but we're at least getting into the range. If the CMB is telling us now that it takes the measurements of the electron optical depth are saying that you start to see electrons about 500 million years after the Big Bang, give or take, and we're at 1 gigayear. That means that we only have like a few 100 million years to play with now between when that process happened and when we're able to probe using this methodology. Okay, so what's the actual program that we've been doing with FIRE? So there's 2 sort of large programs that we've been pursuing in parallel. One is to look for this triply ionized, this carbon-4, at redshifts greater than 5.5. And the other is to look over a wider range in redshift from 2 to 7 for magnesium-2. And remember, just because we call them those kind of absorption systems because that's how we identify them, not because that's the only ion that's there. Okay, and we like both of these because they're resonant doublets, and so there's a pair of lines that always have the same velocity spacing that we can use as a template to identify. Because otherwise, if you only see a singlet, you don't know if you've correctly identified a line. So it's just a matter of convenience. So we find them that way, but then we study all the different other transitions that present. Before fire, there really wasn't an infrared spectrometer that had the sensitivity to do this. We've been doing that since then, and then X-Shooter came along around the same time, and we've both been working on this problem. I think we've been doing a more sort of concerted effort at assembling a large sample of high redshift quasars, but they're both good instruments for this. But just to give you some sense, when we turned fire on, we'd observed 3 sight lines at a redshift beyond 5.5, and there had been no surveys for magnesium-2. And in the intervening years, we've now observed, actually this is up to 43 sight lines now beyond a redshift of 5.5, and we're over 100 for this magnesium-2 survey. And so this is actually starting to get to be respectable in terms of assembling a statistical sample, which is, this was sort of in the postage stamp collecting phase, but it was interesting early reconnaissance. But now we can actually start to say something about trends. And then just to give you a sense of other things in the literature, including my prior work, all these other papers were based on these same sight lines. But now we have a much larger path length. So this is the co-moving path length. It's sort of like the line of sight distance where we could see carbon-4 adding up all of our sight lines. And these are previous things that were in the literature. And now this is the total survey. The purple bar is where we are now using these fire sight lines. And so I just want to give you an overview of some of the things that we've been discovering from those observations. I should mention that we've benefited a lot. At the time that we turned fire on, there were many, many fewer of these things known. So we're very lucky that people have continued to survey the sky. And in fact, the emergence of infrared sky surveys have made this much more efficient because otherwise you find a lot of brown dwarfs if you're just doing optical surveys because they look a lot like high redshift quasars. But the folks who have worked originally in SDSS, but since then Pan-STARRS, UKIDS, VISTA, and the CFHT have all done surveys such that this is just a selection of a few of our favorite sight lines that we've observed over the years. And of these, the bottom is the only one that was known at the time that we put fire on the telescope. And so this is still a growing industry, and people are discovering these. So there's actually been a nice cycle. Some of the people that were on that first page of my collaborators are folks at MPIA who searched through all these surveys for these, and they're interested in the properties of the quasars themselves. And so every semester, I always get the new candidates, and then we can update that. It's a fairly efficient process. And so these are ones that are going from redshift of 6.3, cranking up in redshift to about 7.1, roughly. So this is the famous one at 7.1 that has a possible Lyman alpha damping wing, although I'm not going to talk about that today. But we have definitely been the beneficiaries of this. Okay, so program number 1 is looking and doing a systematic search for high redshift carbon-4 doublets. And the reason we started with that is it is actually by far the most common thing that you see when looking for heavy element systems at low redshift. And when you do a systematic survey, I don't want to go into all the details, but we spend a lot of time. It's actually, the easy part is finding the systems, and the hard part is figuring out what you didn't see, and which ones of the things that you saw were just false positives, because in the infrared, I don't, it's kind of a mess. The sky, the foreground sky, it has hydroxyl features that are much, much, much brighter than the objects that you're interested in studying. And they introduce noise spikes at sort of regular intervals that can be confused if your sky subtraction isn't perfect with real absorption lines. And so we spend a lot of time injecting fake signals into our data and seeing what we recover and doing all that. And so without going into it in great detail, you can get a sense of the kind of structure that's in the night sky. So this is the completeness as a function of redshift as you go out in redshift space this is a function of strength of absorber. This is a rest frame equivalent width. And by the time you get out to an angstrom and equivalent width, we're complete over much of the survey. But there's also a lot of structure in redshift space, and that has it's basically a measure of the structure in the night sky. So in areas like this is the area between the there's a nasty absorption feature that sits between the Y and the J bands, and that sort of rears its ugly head here, so it's much harder for us to see anything that's not really strong, and so on and so forth. But we can see things. So as I said, what we're looking for are doublets. And here are just 4 examples of absorption lines at 4.8. This is redshift 4.82, redshift 5.92, 5.74, 5.72. And so it looks pretty good. The data are not, signal to noise of 1,000. But, it's redshift of 6, right? And so I'm happy to go head to head with anybody who's observing galaxies at that redshift. Since this is only a couple hours of integration. It's the standard thing with quasar absorption lines that you can get much higher signal to noise, but you don't have full information on the emission from the sources as well. So you have more limited information, but you can do it at much higher redshift. So after having gone through all of the sight lines that I mentioned, there's roughly 42 sight lines, 43, I think, that we have surveyed now for carbon-4. And we found 58 carbon-4 systems that we're very confident of. And we've done these systematic tests for the completeness of our sample and its purity. So completeness are the things that we should have seen but didn't, and purity are things that we shouldn't have accepted but did. And we've characterized all of those things. And then we use those, even though I can't tell you in the sample which exact system is the one that is the false positive or something like that, we can statistically correct for those things. And construct an evolutionary history of how this stuff changes with redshift. And the thing that's interesting, so these are the reasonably strong carbon-4 systems, and they peak around a redshift of 2 or so, and then this sort of follows through the optical range, where they change by about a factor of 2 over the range that has been probed by SDSS and high-res and other optical. So we used SDSS for this one because it has the largest number statistics, so the Poisson errors are very small. But you get basically the same result if you use high resolution spectra. And then in the infrared, we're out here going from redshift roughly 5 to 6.5. And what you see actually is quite striking. We've started by surveying for carbon-4 because it was the most common thing, right? Because remember, I showed this is the carbon-4, and the inner part that had carbon-2 is much smaller that sits in there. And we said that because that has the largest cross-section, it is the most prevalent. And so we thought that we would start by searching for those, but in fact, by the time you get out to redshift of 6, the incidence rate is down by about a factor of 25 from what you see at lower redshift. So you can look after one spectrum after another and see nothing. It's actually quite discouraging after a while. But we've just become accustomed to that. The things that are completely pedestrian at redshift 2 are very rare by the time you get to redshift of 6. In fact, there's only one beyond a redshift of 6 that we know of at this point that's not inside the quasar itself or immediately next to it. And it sort of raises the question whether what's happening here, so you can think of it 2 ways. One is that it could be that the number density of galaxies is just going down, but we have counts of those from other methods. Or it could be that the cross-section is going down here. And if the cross-section is going down, is it the case that what's happening is that the carbon actually subtends a smaller solid angle on the sky, and so your odds of hitting it are lower? Or is it the case that what you saw here is carbon-4, as you approach the epoch of reionization, it turns into carbon-2 or other ionization species? If you just have one ion that looks like this, it's hard to say. But it could be that basically what's happened is you've inverted because the density of the universe is getting larger. And the volume number density of quasars is going down in a way that actually could conspire to take away the high energy photons that you need to make carbon-4. But this is actually a degeneracy with this particular measurement of just a single high ionization line. But the fact remains that you're down by a large factor. That's the thing to take away. Now, if we look at the low ionization gas, we sort of got that for free. That's not why we intended to go and survey these high redshift quasars, but when we do, it's just as easy to look for magnesium 2. In fact, when we started, we couldn't go to the highest redshifts in magnesium 2 because it, strangely enough, even though the rest wavelength is 2,800 angstroms, it's in the K band. And so at redshift sort of 5 to 6, which is the highest we had when we started, we were between the H and K bands, but now that there's things going out to redshift of 7, we can look for Mag2 in the K-band very easily. And the fact is that we see it much more prevalently than, with much more prevalence than you would see carbon-4. And we've surveyed more sightlines for this because we can do lower redshifts and we have a broader redshift range. So nobody had ever looked for Mag2 beyond a redshift of 2, but now we've done redshift 2 to 7 in a methodical way. And we found 282 new absorption systems. And this is just a menagerie here, so you can see that, again, it's identified as a doublet. Each one of these is a doublet at a particular redshift. So here's one at redshift of 2.46. The point is not to show things that are particularly noteworthy here, other than to say that we find many more of them than we do for the carbon-4s. Part of that is the larger redshift range, but it's also, as you'll see in a minute, just a difference in how they appear. And the other thing is that when we find these things in carbon-4 or in magnesium-2, we get coverage of all these other ions. So we get coverage of carbon-4, iron-2, aluminum-2, aluminum-3, silicon-2, oxygen-1, all these other things. It's just that this is how we find them. But in contrast to carbon-4, it doesn't seem that those are going away. So unlike the carbon-4, the magnesium-2 actually does persist well beyond a redshift of 6. And there's two plots here. The two panels that I show, these are for the sort of garden variety magnesium-2s. These are similar to the better things that you could detect with Sloan. So we actually have somewhat better sensitivity than most low redshift magnesium-2 surveys. And so we can match them up one for one with what people have done. And because you can see magnesium-2 all the way down to a redshift of a few tenths, we extend our fire points are these circular ones that are over here. And then these are different ground-based surveys that have been done going down to a redshift of a couple of tenths. And what you see is that the co-moving number density, so this is the number per unit path length through the universe, the number you intercept along that skewer, is statistically indistinguishable from something that doesn't evolve between a redshift of 0.4 and 6.8, which was a little surprising to me. But the point here is that unlike carbon-4, it doesn't seem like those things are going away. Now, the stronger ones, if you look at very strong ones, there's some circumstantial evidence that we can get into another time that, that links them with star formation outflows. And indeed, the number density of those traces the star formation rate density of the universe. It sort of goes up and peaks around a redshift of 2 and declines toward higher redshift. And that's something that's interesting, where you may actually be probing the outflows directly. But I actually find it somewhat more remarkable that we see regular magnesium-2 systems out to the highest redshifts where we could look. Now, at low redshift, we can go back to the question of what are these things. At low redshift, it's always the case that when you see a magnesium-2 system, it's really in the halo of a galaxy. These are two examples of such a thing. So here's a quasar, where if you look in the spectrum of that quasar, you see magnesium-2. This is just one of the two doublet components. And then if you look at the spectra of these two galaxies that are nearby, their rotation curves actually intersect with where the velocity is here, and they're at the same redshift as the magnesium-2 absorption. And so the idea is that this is the stellar halo, or sorry, this is the half-light radius roughly of the galaxy, but then there's an envelope that's roughly this large that has magnesium-2 that's filling it. And likewise over here, here's a quasar, and here's the foreground galaxy that's in front of the quasar, absorption here in magnesium, and then it matches up with the rotation curve of that galaxy. Okay? So again, the halo is much larger than the galaxy. And here's another way of quantifying it for many, many systems here. So this is a log of the impact parameter. So if you look at a large sample of galaxies and search for magnesium-2 near it, you'll find that within roughly 100 kiloparsecs, it's reasonably common, although not always. You get about half the time you get a hit, half the time you get a miss. And that as you go towards the inner part of the halo, the equivalent width goes up. So it's stronger absorption the closer you get to the halo. It's no big surprise. But the point is that wherever you see a Mag2 system or absorber, there's always a galaxy nearby. And then we ask the question, well, could this hold at high redshift? So we see these things to very high redshift. And yet, the things that you see at low redshift that have Mag2s, those are many of them are well-formed disk galaxies. But out at redshift 6, do you have well-formed disk galaxies? Not in that same way, I wouldn't expect. But we can at least do some statistical tests and imagine, suppose I take luminosity functions either from observations or from, you could take a mass function from a simulation. In this case, we took a halo mass distribution from Illustris and then said, say I just paint a bubble around every halo that has mag2 going out to 100 kiloparsecs, with all the scalings that you get from the low redshift observations. And then I scale those to halo masses that match up with low redshift and produce the correct number of absorption systems, and then let it evolve out towards high redshift. Do I predict the correct number of magnesium 2s that I actually observe? And the answer is no. You miss by a huge amount if you just say I'm going to fix them. The halos below a certain mass don't have magnesium 2, and above that we populate it as we do at low redshift. Then the problem is by the time you get to high redshift, all the halos are lower mass, and none of them are holding onto their magnesium 2. And so that doesn't work very well at all. In fact, people had proposed such a model early on, but these data rule it out. You may be able to do somewhat better if you take into account, instead of a fixed halo mass, if you cut off at a fixed star formation rate, because a fixed star formation rate, let me see if I can get this right, as you go to higher redshift corresponds to a lower mass. And so that provides a natural way to give you a lower and lower mass cutoff. So you're producing magnesium 2 in lower mass galaxies as you go to higher redshift. And that does somewhat better. It's not perfect, but it does sort of an okay job. But the point is just that you've got to be able to produce stuff in smaller galaxies as you go to higher redshift. But all galaxies are smaller. So that may be okay. But the thing that sort of strikes me is more just a qualitative statement that if you're really going to have magnesium 2 associated with intra-halo gas, I like to call this circumgalactic medium the intra-halo medium in some ways. It may be that you're enriching this as you're forming the galaxy rather than a situation where all the matter accretes into the central part of the galaxy, forms its stars, and then blows stuff out into the halo, which then you can see. And because by the time you get out to redshift of 7, there's not a whole lot of time to free fall in, form the galaxy, and then blow stuff out. Now, if we have access to Illustris, which we did because we've been talking with Paul Torrey about this, who's a Hubble fellow over at MIT, why not just go straight to the Hydra simulations? You've got access to the gas box, and you can shoot sightlines through that and make magnesium 2 systems as well as anybody. But there's reasons that this is challenging and that you might not want to do. And I don't always talk about this, but I thought I might spend 3 slides talking about it here. I've got just enough time to do it. And the reason is as follows, that we think, you remember that first movie that I showed of a galaxy that was forming, and you saw that as it was forming, you sort of got a smooth hot halo that filled the inside of the virial radius. But that hot halo is not going to produce magnesium 2s out to 100 kiloparsecs. The hot halo is going to be seen in other species like oxygen 6, or things that are even more highly ionized. So you've already torched away all the magnesium 2 at those temperatures. And so that's actually something that it may be that the simulations are not really resolving correctly, and we're quite sure that they're not. And one way to see it is as follows. So we can just, it's easy enough to make these simulations and predict the number of absorbers you should see as a function of their strength, their equivalent width. And for 3 different runs that were used for convergence tests, you can see the 3 predictions that you would get. And these are the numbers of systems that we observe. So we see many, many more systems at high equivalent width or high strength. There's stronger absorbers in the real universe than there are in the simulations by a huge factor. We can talk about why that is in just a minute. There's another thing that's a little bit funny about the simulations, which is that if you plot up in the temperature density plane where magnesium 2 should appear, there's a certain range of temperature and density that it likes, and that's sort of down here. But that's actually where, for convenience, the simulations impose a particular equation of state to simplify and speed up the calculations. And so we may be sort of missing out on the area that's of interest for this kind of CGM physics. And that's fine. I mean, the simulations weren't designed to do that. But but it's interesting that it's not, oftentimes people think you can just do this, and it's not so simple. We think actually what the simulations are missing here, we think that actually they've got roughly the number of galaxies right, but it's the sort of details of what's happening inside the halos that are probably not quite right. And what we think is missing is that there's both spatial substructure in these, but actually more velocity. So what's not needed is more column density. What's needed is to stir up the gas, because you create equivalent width by taking it and spreading the system out in velocity space. So if we basically took a halo, this is actually a raw lustrous halo that we used as an example, and then we just artificially broke it up into smaller halos and then gave them all different velocity kicks, then you can actually take the original line, which is this red one, and then as you give them successively larger kicks, they will actually reproduce the correct distribution without having to change the overall number of galaxies or anything like that in your simulation. You're just stirring them up a little bit more. And we think that that's probably what has to happen. Now, that's a kind of ham-handed way of fixing this problem. So we've fixed it, but we haven't said anything about physics. All we've done is take the bottle and shake it. It's sort of in the early days of doing this kind of work, but it's kind of fun to speculate about where you could get some of those velocities from. And one of the things that we've been following is the literature that people have been developing for galaxy clusters, where in the midst of a hot halo, you can actually get thermal instabilities. If you get a little density perturbation, then it can cool quickly and then coalesce into a small ball. And once that happens, it's not going to want to sit out in the outer halo. Once it turns into this little nugget, it's going to fall back down towards the center of the disk. And those little nuggets actually might explain a bunch of things that have remained mysterious about magnesium-2 absorbers. For example, when people, you can see them out 100 kiloparsecs from galaxies, and you've got a 50% chance of hitting one. But when you look at gravitational lenses, and then you see, at what point as lenses get further and further apart, do they start to become decoherent in magnesium-2? The size scale is on like tens of parsecs. And if you do modeling on the line of sight sizes of these things, again, it's tens of parsecs, and yet they cover an area hundreds of kiloparsecs in size. It means there has to be a tremendous number of small little lumps of cold gas that you can see. And the other thing is, how do they acquire their velocities? Well, it could be that some of the velocities come from going up and down in the halo. So let me just start this movie to give you a sense of what this would look like. So this is actually just a tube that we made using a repo, where the galaxy is down here. It actually extends up 250 kiloparsecs. But what you're seeing is we've put the cooling recipe into this so that little blobs can cool out of the hot halo when they have density perturbations. And then those, you can see that those start to rain down until in some cases they're entrained by stuff that's rising, hot stuff rising out of the disk. But the point is that you get a lot of little clumps of things. Those bright knots here are the things that you would see in magnesium-2. And they can cover a non-negligible fraction of the area on here without themselves being very large. And it may be the case that this is in the velocities stirring here is the gravity is doing some of the stirring for you. That basically things that we thought of on the net, we've enforced in this simulation that the halo is in net hydrostatic equilibrium, and so the temperature profile. So there's a beta profile density and then a temperature profile that enforces hydrostatic equilibrium when averaged azimuthally around this system. But locally, it can have departures from that. So, I am not necessarily the person that has the most expertise on these simulations, but I'm interested because it's, besides the fact that it's fun to watch, like a lava lamp, it's, this actually sort of looks and feels a little bit like it explains some of the weird things in the observations that we're seeing. So this is, again, an Arepo simulation. It's got a mass resolution of 500 solar masses. 4 kiloparsecs across here. It's very computationally expensive to do a much larger simulation than this. Okay, let's go back to the data for the last little bit on this. We've said that magnesium-2 persists in the universe out to the highest redshifts. And the question is, when you look at all the other things that are associated with it, are there any discernible changes in its properties? Meaning, if I see a magnesium-2 system and ask, how much carbon-4 is there associated with that? Or what's the what's the equivalent width of iron-2? Can I see any difference? And for a long time, the answer was no. Up until about, our first crack at this problem only went up to a magnesium-2 redshift of about 5.2, because that's when it falls into the HK gap. And up to that redshift, we can split things into systems that have a redshift below 2 and a redshift above 2. And things that have a redshift of below 2 are blue on this plot, and above redshift 2 are red on this plot. And then you can almost ignore the orange ones are from Sloan, so they sort of fall in the same area, but a lot of them are upper limits because Sloan's not as sensitive. But the main point is that for all of these different ions, the blue and the reds basically overlap with each other, which means that if I identified something at any redshift, it was a little weird that the absorption line systems kind of look the way they do at all redshifts. Even a fairly seasoned observer would not necessarily, they would be challenged to tell you, if they had a sort of modest signal-to-noise spectrum, to guess what the redshift of a particular system was. And the thinking was that there was something that was sort of local, that, again, it's how it presents. The things that you see, the carbon-4, the magnesium-2, if you see it and select it one way, you're seeing things that are in a certain range of temperature and density and ionization that are always going to look sort of similar to each other. And so there really was no change. So this has a lot of upper limits, but you can actually combine the upper limits and the data points using survival statistics and show that this is the cumulative distribution of the ratio of each ion relative to magnesium-2. And you see that these are all overlapping almost perfectly at all different redshifts. There's a little bit of a change here, but it's not much. And so that's sort of a more quantitative statement. And we did 2 sample tests and showed that they were indistinguishable. Now, that's a little weird, too, because I said that the carbon-4 must be in decline by the time you get to very high redshift. And so eventually, actually, if this keeps going down and the magnesium-2 is flat, there have to be more magnesium-2s than carbon-4s, which is opposite to what our intuition said at low redshift. And in fact, at this very highest redshift, once you get out into the K-band, that happens. Okay, so this shows, again, this is a function of where your threshold and your cutoff is for things that are observable. And so it'll change a little bit, but the basic result is the same. That by the time you get beyond a redshift of 6, there's actually more magnesium-2 than there is carbon-4, which is, to me, feels weird still, but that's just the way the universe is. But it also suggests that if this is true, there must be systems that have low ionization, but no high ionization absorption. Okay? And we hadn't found those before, because before the surveys had always been in either carbon-4 or magnesium-2, but they didn't cover all the different ions that were relevant. But now that we've got a lot more of these things, we're starting to see some that are interesting. And I will just show 2 such systems. They're chosen for 2 different reasons. One is that this is a very high signal-to-noise one that's interesting. The other is that this is now the record holder, a recent record holder for the highest redshift absorption system known. So this is at redshift 6.84. And we can see, so just the way that I've arranged this now, I have stacked so that I shift each ion into its rest frame. So a value of 0 represents the ion that's shown over here. So a redshift 0, you're seeing absorption from magnesium-2, the first element of the doublet. And then here you're seeing it from this element of the doublet. And what you're looking for is areas that are in this little shaded region, looking for lines that tend to line up with each other. And that gives you high confidence that you're actually seeing something in the data. And so in this one, at redshift 6.84, we're seeing magnesium-2 in 2 transitions. It's noisy, but then you're also seeing iron-2 2600, silicon-2 1526, carbon-2 1334. These are all, I've arranged them in order of increasing ionization potential as you go up the chart. And what you see is low ionization potential, you're seeing these lines, and then they start to disappear. And then by the time you get up to the top, the carbon-4 is not there. And that's a system you would almost never see at low redshift. And here's a better example of this, which has even basically a perfectly neutral ion. This is oxygen-1, and here there's no doubt that you see it, right? This is highly statistically significant. There's the magnesium-2, again, increasing ionization potential. There's iron, silicon-2 1260, that's really weak for that, it's amazing. There's carbon-2, and then you see these insane limits on carbon-4. There's just no carbon there. And so what this means is that, what's interesting is that these are not isolated cases. Beyond a redshift of 6, so I think we know of about 10 systems beyond a redshift of 6, 8 of which look like this. And essentially no systems, or very small, maybe a few percent look like this at lower redshift. So it seems that at high redshift, galaxies are losing their highly ionized envelopes. Here it is if you just want to make this on that same plot that I showed before. So the red and blue are at redshift 2 and higher. Here are the two things where we detect carbon-4 beyond a redshift of 6, and here are all the other ones. So they clearly fall below the locations where the rest of our sample are. So the black points are the ones beyond a redshift of 6, and the red and blue are redshift 0 to 2 and 2 to 5. And here's where they would fall in that equivalent width distribution. So I don't have the equivalent width distribution, but you can see that these are the ones that completely overlapped before, and there's two that kind of work, but then all these ones are quite low. So you would never see a ratio that looks like this. So this is quite unusual. Okay, so that's one of the main sort of things that's starting to emerge in terms of trends from these quasar absorption line surveys, is that the galaxies, by the time you approach the epoch of reionization, they're losing their highly ionized gas envelopes. We're accustomed to, at low redshift, we learn a lot by looking at comparisons with the galaxies that are near here. So what are we doing on that front at high redshift? Well, it is a lot harder. Remember, we're talking about redshift 6 to 7 here. This is not a walk in the park. But even though at low redshift we've learned a lot, this is, from Cos halos, an example of the kind of information you get by looking at a quasar spectrum, and you get all this, and then you see the galaxy there. We'd love to have that. Or if we knew the impact parameter to all of our galaxies, this is at redshift of 3, work that Chuck Steidel has done, and he knows the equivalent width as a function of impact parameter. We're not doing that at redshift 6 yet. But there's a few things that we're working on to try. So one is that, and I'm not going to tell you other than what we're up to here. I'm not going to give you results. One is that we've got a program with Magellan for some of our quasars at lower redshift, sort of 3 to 4.5, to do multi-slit spectroscopy the same way that Steidel et al. Have done with Keck. And we're supposing that the Magnesium 2 is circumgalactic, but we don't have the offending galaxies, so we're trying to find those. It's very painful. This has been a several-year project, and I was telling Lars before that by the time you reach several years, that's about how long it takes to build an instrument. And so once you reach that threshold, you might as well build the instrument that you wanted to do that project. And so we're working on that at MIT, where we would like to build an integral field spectrograph for Magellan that instead of taking spectra of just the things that are shown in the slits here, you can overlay on a CGM field that looks like this. And so we're going to put a fiber bundle on the sky that samples 1 by 1 arc minute at 0.75 arc seconds, and take a full optical spectrum of every point, every little circle that's on here. This would be about 8,000 spectral units. And we feed it with a micro lens array to get a 90% fill factor. So this is my particular interest, is doing this circumgalactic medium science at sort of modest redshifts. But there's lots of other things you could do with it, including following up transients with LSST. That's a big, or following up to get redshifts for clusters discovered with the South Pole Telescope. So like FIRE, so FIRE is here on Magellan, and this would sit at the next port over from FIRE. And there's a fiber feed here that would feed 4 different spectrographs that sit down here, each of which is only about yay big. And that's sort of a new model for building some of these instruments. And then here's a prototype of the lenslet array. You can see these are the 8,000 lenslet units. And then you plug fibers into a thing that aligns with those. So that's one of the things that we're working on to try and improve the fact that we only have the absorption line measurements at these redshifts. Nobody's done any, there are 0 galaxy absorber pairs beyond a redshift of 4. And we'd like to improve that, but we need to have more efficient instruments to do that. I'm tired of doing photometric selection and making slit masks and stuff. We just want to, boom, just do it. If you're going to integrate, make it count. So, of course, even that's not going to help you at redshift 6. Really, the only game in town for that is that you've got to use James Webb Space Telescope, which fortunately looks like it's going to fly. But if we really want to make progress out at those very highest redshifts, that's the only way to do it. And fortunately, it looks like we're going to have the opportunity to do that, inshallah. We've become involved in a GTO survey that's going to be done with PI Simon Lilly using NIRCam to do a 110-hour survey. He's going to use this entire GTO allocation towards this, and we're going to turn over all of our quasars for our best and brightest fields to do this. And we're going to focus with 10 hours of integration on a 250 kiloparsec region in the middle, in this green square. And then there will be a flanking field that goes out to a 10 by 7 megaparsec area to study transmission of H1 in the IGM. And because these fields, unlike the frontier fields and things, these have never been imaged for pre-selection, so we can't use NIRSpec yet for these, even though it's more sensitive. We can go with NIRCam and get slitless spectra of everything, and their emission lines are going to fall out here in the red bands of NIRCam, and meanwhile we'll be pounding away in the blue filters of NIRCam, so we'll get ultra-deep broadband images that are deeper than 29th magnitude in J and K that we can use later on to go and follow up things. And so we'll get 2-hour depth with JWST everywhere out here, and 8 to 10-hour depth on each of 6 fields that have the brightest quasars in there. And this is really, I think, the best hope for ever trying to do galaxy absorber work at these redshifts. I don't think there's any other way that it's going to be straightforward. The last thing I'll say is that also this is an interesting field for ELTs, but it requires good IR spectrometers. I hope I've convinced you that IR spectroscopy is necessary to work in the epoch of reionization. So we know that Magellan Fire is actually read noise limited for a 6.5 meter telescope, and since it's the same size as JWST, we know that JWST will be read noise limited, except at very low spectral resolutions, and that they're working hard to try and combat that. But it's actually an area where the ELTs will do reasonably well, even in the seeing limit. And so we've designed an instrument that could go on GMT to do this, but it remains to be seen whether something like this could be built. But this is what it would take to make progress in this field. And the quasars are there, but we just need to have the right tools to look for them. Okay. So that's all I have for today. My time is up, so I should get on with it. But let me just summarize the take-home points that I'd like for you guys to remember from here. One is that the continued discovery of these quasars at redshift 6 and now exceeding 7 it's really improved our ability to do absorption line work, that from doing the occasional interesting thing, these exploratory early observations, it's really, it's becoming a statistical ensemble now. And that the probability of intercepting these highly ionized carbon-4 systems is going down fast as you get closer to the epoch of reionization. But that the low ionization systems are largely unchanged. And that means that some amount of enrichment was happening in circumgalactic gas very early in galaxy formation. How that happens is a little bit unclear yet, in that we know that there's physics missing from the simulations, probably because of resolution effects, and also they may be missing velocity structure that comes with sort of cooling that you can't resolve in a cosmological box. But the galaxies that we see must be losing their highly ionized envelopes at redshifts beyond 6, because we're seeing these systems now that have low ionization but no high ionization, which is not seen at low redshift. And that we're trying to make some progress on the rest of it by building an integral field spectrograph. JWST is going to be very helpful for this, and ELTs as well. And so that's a sort of a summary of where we stand sort of 7 years after fire, and I'm happy to take any questions. So thanks for your time and attention.
Great, thank you very much, Rob. So, questions?
Are you supposed to say anything about the trends and elemental abundances as you go through, or is it too complex based on the modeling requirements?
You can say some, especially in situations where you have the similar ionization potentials. So, for example, we could. One that we will be doing is the alpha over iron, where what's a proxy for that is magnesium over iron, because there's reason to expect that might change as you go to very high redshifts. And because the ionization potential of iron 2 and magnesium 2 is very similar, then you don't have to worry quite as much as you might otherwise about some of those differences. And you can do the same thing for silicon. It gets a little dicey if you need to compare things that have very different ionization potentials. Because then you have to do a correction that's model dependent. And we can do that, but I'm pretty cautious about doing those sorts of things, especially when you approach reionization, when you have to worry about radiative transfer effects and things like that. But as long as your ionization potentials are similar, I think you're at least, it's defensible.
Yeah, to get the 100 or so systems, how many quasars did you actually have to look at?
Well, we looked at 100 quasars. For magnesium 2, 108 quasars, and then we look, we found 280 systems.
Oh, so. Okay.
Yeah, so a few per quasar. But with the, for the carbon 4, it's much worse. So, we looked at 40 sight lines and we found about 50 something absorbers, but most of those were at redshift 4. So it's like for redshift above 5.5, you get sort of off the cuff, I would say, 1 carbon 4 for every 3 or 4 quasars that you look at. It's pretty painful. So it's a good thing there's magnesium too, otherwise we would have given up long ago. But it's weird. It's very different. At low redshift, if you take a high-res spectrum of a redshift 3 thing, you'll find 5 carbon 4s per spectrum.
Are the carbon 4 and magnesium 2 systems always mutually exclusive, or do you sometimes see both?
At lower redshift, if you see one, if you see magnesium 2, you almost always see carbon 4.
So does that mean the carbon 4 is not coming from further out?
No, it's that you're seeing sort of 2 things nested inside of each other. And so a way to think about it, yeah, so you will see often carbon 4s without magnesium 2 because it has this, it traces lower density stuff, and so it's more extended, but you might miss the little clump in the middle that also has the magnesium 2. But if you see magnesium 2, you're probably also, you're looking through it. So when you select on magnesium 2, you always see carbon 4 until you get to redshift 6, in which case you rarely see it. So what's happening is that outer thing has changed somehow.
More? Well, if not, let's thank Rob again.